Okay, picking back up in 12.4, the bottom line is not every problem will allow us to use the basic comparison test. Sadly, as I went back to the pictures up above, let's just real quickly go back to that. Let's just say that, our red stars for number 2 here, what if they were always underneath a divergent series? What if the red stars had to be under, or these black stars? Are we guaranteed that the black stars would go off towards infinity? Not necessarily. Like if you knew that B sub n diverged, and A sub n is smaller than B sub n term by term, these black stars would be under the blue dots. We don't know what's going to happen. We don't know what happens to this series A sub n. So that gets very frustrating. By way of comparison, you could say, what if, in number 1, what if you're told that B sub n is convergent, but I'm telling you that A sub n is bigger than B sub n term by term? In other words, your black stars are bigger than the blue dots. Who's to say that the black stars might not launch off towards infinity? Maybe they're going to level off, maybe they won't. The bottom line is we don't know. We don't know if that series A sub n converges or diverges. So the basic comparison test has to fit those 2 original pictures with those relationships. You're strictly working with Roman numeral 1 and 2 here. Adding to that, we can see that you very well could have multiple changes occurring as you try to create a second series. So very often as you omit things in the previous problems, you only had to omit one term, and the result was a power series, a P series, or a geometric series. Here we're dealing with some problems perhaps where things could get more complicated. So let's read the limit comparison test. It's a second test that you can use. If A sub n and B sub n are positive term series, again, very critical. We can't use this if there are any negative terms in there. And if there's a positive real number C, such that the ratio of A sub n over B sub n as n goes to infinity in this limit is equal to C, it's a positive real number, it's greater than 0, then either both series converge or both series diverge. In other words, the behavior of the 2 series will be the same. How is this a huge help? Well, if A sub n is written as a fraction, if it's a quotient, to determine that second series, delete all the terms in the numerator and denominator except those that have the greatest effect on the magnitude. Think end behavior. And I'll tell you what, your B sub n, outside of doing some end behavior, you want to see a P series or a geometric series in the end. Take a look at A sub n with me right here, a little bit of practice. Look at the numerator, 3n. You could get rid of the plus 1. Down here, 4n cubed. That means anything smaller than that we can omit. What are we left with? 3n all over 4n cubed, which would really be 3 over 4n squared. You could factor a 3/4 out of a series and really be left with the P series, 1 over n squared. You'd be able to know that that series of B sub n would converge. For the next one, you could drop your 2n and the 7, and you could say, well, wow, that would leave me with 5 all over the square root of n squared. Again, assuming that we're dealing just with positive values of n here, then the square root of n squared really is just an n. And you could see you'd actually be left with a harmonic series with a 5 multiplied in. Let's do this last one. The numerator could drop the plus 4, drop the minus n, drop the minus 1. What's the big theme? You're seeing more complicated formulas where you couldn't just omit one term. we're required to drop a whole bunch here. And what's left? Well, you'd have the cube root of n squared. Down below, you'll have 6n squared. This, by the way, is n to the 2/3 all over 6n squared. And you could say this is 1/6. Here we could do some subtracting. 2/3 minus 2. Well, 2, of course, is really 6 over 3. 2/3 minus 6/3 then would be negative 4/3. Another way to look at that, 1 over 6n to the 4/3, a convergent p-series when you put sigma in front of it. Well, why do we do this? Again, the ultimate goal is once you get your new series, what you'll do is you'll set up a ratio, take the original problem divided by the b sub n, take that limit as n goes to infinity. If, it's a big if, you arrive at a positive real number, you can say that the series behaved the same. If you go to infinity, that doesn't count. If you go to 0, that doesn't count, of course. You need a positive real number to be able to say anything here. So let's take a look real quickly at some problems. For a sub n, for number 3, a sub n, we can think of that as 3n minus 2 all over n to the 3rd minus 2n squared plus 11. Let's take care of some n behavior here. And we can say b sub n is going to be 3n, if you drop the minus 2. Drop these other two terms down below, you'll have n to the 3rd. And cleaning this up, you'll get 3 all over n squared. Which, by the way, that is a series. You put sigma in front. That's a p-series, which will converge. But the limit comparison test will say, okay, what you really need to do is look at this limit of a sub n all over b sub n. So if I may, I'm just going to write this thing out. Take your numerator of 3n minus 2 all over that n to the 3rd minus 2n squared plus 11. We're going to say divide all that by 3 all over n squared. And this is definitely the case where dividing by a fraction is the same thing as multiplying by its reciprocal. So I'm going to take a sub n and then multiply that by n squared all over 3. And guys, if you're really, really on your toes here, you're going to not even have to distribute all of this in to know what you're arriving at. Be my guest. I mean, you can definitely do that. But the big question I always want kids to be aware of is, what would be the biggest power of n and the number in front of it if we did multiply that out? The top, I hope you could agree with, would be 3n cubed. Likewise, down below, we'd have 3n cubed, and that's just end behavior. So 3n cubed divided by 3n cubed would be 1, which is a positive real number. That's what we're looking for, a positive real number. So now what? I'm going to say that this series of b sub n is a convergent p-series. So now what I'm going to say is, by the limit comparison test, the original problem converges also. The behaviors will be synonymous. They're going to be the same. Again, the limit comparison test is only going to be effective when our limit will arrive to be a positive real number. Last one, for number 4. You can say, well, let's see, it looks like I've got a sub n is this 1 over radical n squared plus 19n. B sub n, if you're really thinking about it, you can drop that plus 19n and you'd be left with 1 over the square root of n squared, which is 1 over n, which is one of the most famous series of all, a divergent harmonic series. So, where are we going with this? Let's take the limit as n goes to infinity of a sub n all over b sub n. And that will be the limit of this 1 over radical n squared plus 19n divide by 1 over n. Now, as we clean this up a little bit, I hope it's pretty clear to everybody that, again, dividing by a fraction is the same thing as multiplying by its reciprocal. But this is why BC Calc teachers stress n behavior from the beginning. This is going to be a daily occurrence for us working out limits. We're going to say, okay, n goes to infinity. Really, that plus 19n is inconsequential also. And the square root of n squared is just an n. And n over n, of course, is simply 1. So again, you're going to get a limit that is positive. What that means is we can use the limit comparison test. This series of b sub n, 1 over n, is a divergent harmonic series. You could also call it a divergent p-series if you'd like. What does that mean? By the limit comparison test, the original problem diverges also. So that 1 over radical n squared plus 19n diverges also. Notice that this is the work that is expected. Even on the AP exam, you don't just simply say, yes, it diverges. You have to show the comparison that is being made. You have to show the limit. You also have to name the test that you are using. And that wraps it up. Good luck.